Hello, everybody. I'm here with Bil Herd. He's an ex-Commodore engineer and a lifelong electrical hobbyist and engineer.
Yep.
He's going to talk to us today about phase lock loops. And is it going to be everything about phase lock loops, or?
No, no, not at all. It's just some of the cool things we can do. We're so used to talking about digital, but here's a semi-analog part that can jump in and help us sometimes.
Excellent.
Oh,
You know,
yep.
today um, PLLs are in all my microcontrollers and my FPGAs, and I just write a little bit of code and I just give it. Sometimes I just drop in a frequency I want it to generate. So, I
Yep.
have 16 megahertz in, I want a gigahertz out. I just type that in.
And the phase delay.
Yeah. And so, why do we care? Why do we care about how a PLL works?
Yep. The phase lock loop, as I was saying earlier, there's digital and there's analog. And, we're going to go down the path that it's all analog. And I used to say it's all analog anyways, because of the ringing and the time it takes there. And one day Headley Davis looks at me and says, "What about quantum?" I'm like, "All right, you get far enough and it turns digital again, but it's all analog." And a phase lock loop, it actually saved my life one time. It threw itself in front of the bus, and I've been eternally grateful to phase lock loops. They're that useful. But in all seriousness, a phase lock loop really did save the day for a 1985 CES show for the Commodore 128. We had a rogue 80 column chip that was asynchronous. Had its own clock. It had its own version of what should happen when. And what happens is he's clocking along, and if you don't know what's happening and that clock transitions, you're clocking an unknown state. And the designer said, well, since it'll happen anyways, no need to correct for it. Well, it's all statistics. So if you synchronize and then have another stage to synchronize, by the time you put 3 or 4 of these together, it actually will give you at least not garbage. It might take one clock longer, but it won't give you garbage. So we fixed that by taking 2 video controllers and phase lock looping them together, so that they're both trying to do the same thing at the same time. So that's kind of what it's useful for. Let me put up a block diagram of phase lock loop here. And again, this is modeled after the CD 4046. Matter of fact, I could put up some links and stuff here a little later on.
Can you still buy a 4046?
I did. I just did from both probably DigiKey and Jameco. It's harder to find the data sheet these days because they keep taking you to those alldatasheets.com places. I'm getting a little echo here if you hear me hesitating. Hold on. So you can definitely buy them and get the data sheets. There's also the NE564 if you want to go faster. But the CD4046 is a CMOS only, and then they have an HC4046, and then they put out TTL variants on it. But this part here that's on my bench is a CMOS, and I've already accidentally given it 12 volts while it was on a 5-volt supply. So they're pretty hardy characters, the CMOS ones. They don't go as fast. You actually could probably run them at 200 degrees if you run them really slow. The old CMOS stuff, you can derate the hell out of them and they'll still work. So it's just speed equals time.
Hey, Bill, let's
So,
pause here for a second. There's a lot of
sure.
audio distortion.
From me?
Yeah.
All right.
Oh, wait.
It's
Let's start talking again.
all right. So I was going to say, how is it right now?
It's great right now.
Okay. So is it when I get excited?
I guess so.
Okay. I'll try and not get excited.
No, no, okay. It sounds good now. It was just really quantized there for a second.
If it's quantized, it's probably, at least I'm on the one that's not wireless. The laptop is probably all this network stuff we take for granted these days. So, but the 4046 has in it 2 phase comparators, and we'll talk about the difference in a second, and we can select which one of it is. And out of this phase comparator is a signal, and we'll talk about that. But then we just put it into a low-pass filter, and we make a DC voltage. So quite simply, the voltage does one thing when frequencies are doing what we want, and it does something else when it's just random. We take that voltage and we put it into a voltage-controlled oscillator. And so it's analog. There's a voltage and there's an oscillator. But boom, we're back to digital again right after that. And I'll tell you that that oscillator knows the future. That's what's cool about a phase lock loop. Any other circuit, I have to wait for the clock edge to know there's a clock edge. Oh, there just went the clock edge. But with a phase lock loop, it goes, you know what? One microsecond ago, there was a clock edge. Before that, there was a clock edge. There's another one coming, and it knows when. And that's because of the energy stored in this cap. If you make this an electrolytic cap, this oscillator will move around real slow. And people will do things, if you ever see like a resistor here, or even you'll see a Bessel filter here or something, then they get real complex. That's where they critically dampen it. And by the way, if you ever get a resistor in series with the cap, that's not a simple circuit. It actually goes beyond my math. It takes the 0 off of 0, moves the pole in the other quadrant, and becomes a weird thing real fast. But a simple RC circuit will store that energy of what voltage it was, and so if things change too quick, it'll fill in the gaps. And so I've actually seen a phase lock loop shown like this in the old days. They show a spring hooked to a mass. And what that was, I think did that symbol come in? Yeah, so you can't see it real well. But that was the symbol for inertia. So a phase lock loop has inertia. It knows what it was just doing, and so it'd like to keep doing that. So what we do...
Is that filter, does it have a specific name?
Simple RC filters work good in the ones I use. If you get into radio frequencies, they will do things. They make discriminators out of these, and you know, if you ever tuned an FM radio, and we'll talk about how this would do in FM, so we'll talk about a little bit of analog. They tightly control how wide the signal is allowed to go to capture the VCO and whatnot. So, but for what we're doing, just a simple RC. Otherwise, this is just a bunch of pulses. So this is detected. Coming out of the phase comparators are the errors that it sees between the two signals. So you need something to make it into a voltage. Otherwise, it's on or off, and that's no good. So there's two kinds of phase comparators called 1 and 2 in the 4046, and one is really an exclusive OR gate, just as it's shown there. And it's pretty useless for the kind of stuff I've done. An exclusive OR gate, if you think about it, if I've got a reference signal coming in, the only thing that will make that gate be quiet is an exact replica. If this is too big, there's an error term here and an error term here, and pretty soon this is bouncing all over the place. So it's good for comparing square waves to each other that are identical. We don't do that very often. I wouldn't need a phase lock loop if I had two identical square waves, I'd argue. What the other one does, though, is it looks for the edges. It tries really hard to make these edges coincide. So it will adjust. If this thing is over here, if this frequency, this pulse, it'll bring the VCO until it locks, until it lines up with that. And it does that because it samples the output compared to what you're doing. So it's always looking at what it's putting out versus what you're putting into it, and it's doing whatever it can to make these two edges line up. And that's a godsend, because I know this edge. If I know this edge, I know that edge. And that's why I wanted to show some examples of when that might come in handy here. But first, I thought I'll just show you a quick phase lock loop in operation here. Now, some phase lock loops, the oscillator will run in the middle of its frequency band when there's nothing to lock onto. Others will lay on the low side or whatnot. But quite simply, I've got a clock going into it, and you see the clock coming out of it, and they're tracking each other. Now I'm going to break lock here. There.
So is the top line the signal going into your phase lock loop? And the bottom?
Top line is the phase lock loop free running.
Okay.
And the bottom is now, see, and see how you can't see anything meaningful in there? That's actually the problem we're going to try and fix, because I'll tell you, there's nothing meaningful in there. If you make a clock transition travel right here, and you don't have your setup time and you don't have your hold time, that part could go metastable on you, which means that the unknown state will race around the flip-flop until all the gates inside the flip-flop are in an unknown state. And in the old ECL days, that would actually propagate real fast through all of them and blow the fuse, because now everybody's linear and between, you know, their VCC and VEE. So what I'm going to do is I'm going to walk it down, and it probably won't work, but we'll try it anyways, and get another capture. and you see it trying to do things. It'll try and land on certain edges and stuff.
So you're bringing your reference clock more into the spec of what your
Yeah,
PLLs design?
in theory. So what we saw was a phase lock loop that was previously locked that is now no longer locked. And I may just leave it like that rather than sit here and dink around with it. Let's see if I can get it. And what you can do with this, well, anyways, you saw it earlier. It was they were tracking each other. So what will happen, and this is actually how you tune in an FM radio or something, what will happen is there's a capture range. It will only reach so far to either side, but once it grabs it, it'll follow it, and sometimes try and bring it in. So if we look back at a phase lock loop, let me show an example here. If I have a frequency coming into this, and it's frequency modulated, it's getting shorter and longer, the voltage here is going to be going up and down as if this tracks it. Well, if you put a speaker on there, guess what? You just tuned into an FM radio, a frequency modulated radio. So the frequencies that we're wiggling here appear as a voltage here. So that's just one of the cool things that a phase lock loop will do for you in the digital world.
I think I've actually seen application notes where they show you how to make simple FM receivers from phase lock loops.
Right. And I used to do something back when I did ultrasonics where I would have a frequency, but I would do what's called chirping. I would make the frequency go real fast for a second, then go back to its normal. And this thing here, it'd get upset and it would spike. And I would hook a comparator to it, and I could find the beginning of a pulse from that amongst a whole bunch of garbage by introducing an error. It's kind of like introducing a layer 2 error or layer 1 error on token ring or something like that, where you blow a clock and it freaks out and says, oh, that must be the start of the packet. So you can do the same thing there. So the other thing we can do is clock recovery. Again, if I'm sitting here and this capacitor is saying, you know, I'm at 1 megahertz, I'm at 1 megahertz, and some clocks drop out, he'll start to drift. So the rate it drifts is based on this circuit right here. The rate it captures is also based on that. So it's a trade-off. How fast can I go grab a frequency versus how hard will I sit on that frequency when I have it? I've done this with electrolytics, and it takes a minute for this thing to move around. Or we've done it with very active circuits here, and it turns into an FM radio or something. So that fact that it will hold that frequency, that's that inertia we're talking about. Well, here's an example of why that might be useful. Let's say that I want to modulate a carrier, which means I want to put information on it and I want to broadcast it. Well, I can save a lot of information and a lot of broadcast power, and I can save room on the broadcast band if I suppress the carrier before I send it, which means now it's just the information, but not the carrier it rides on. Well, wait a minute. When this lands back in, I'm talking about a TV set actually, the color subcarrier, it's like, that's great. You got me the color changes, but I need something to compare it to. So once every horizontal line, they would give it 8 color clocks. And this thing would go, that's good. You give me 8 clocks and I'll hold it one whole horizontal line across the screen. And so this becomes our restoring carrier. So what this can do is clock recovery. That's kind of where I was headed with that. It can do, if you give it a few clocks, it can keep going from it. If you give it a whole bunch of averages, a whole bunch of frequencies, like in a Manchester encoding or something like that, it'll find the carrier and stand to this. So if it's noisy, if the clock is actually stuttering and missing out and stuff, or got extra edges, it'll clean all that up. So by virtue of the inertia, whoops, I'm pointing to a screen you can't see, but by virtue of the inertia that's in the capacitor.
Do they ever put any gating circuitry in there to during those 8 clock cycles to set that VCO?
Yeah, I know right where you're going. And, NTSC, I guess, is obsolete. But we used to work our asses off to find the back porch. I'm drawing on a screen you can't see. There it is. Sorry. I don't even think we have sync pulses these days with HD TV and everything. But in the old days, when I was young, we had a horizontal sync, and we had the actual sync, which was blacker than black. This was black, this was white. And we looked for this event to freak out a different comparator, which had to drift around with the video and everything. And on the back porch would be 8 clock cycles of color that we would try and grab to keep this oscillator, 3.5759 megahertz oscillator, running. So it was all about capturing the color subcarrier. And then on PAL, if you've ever heard of PAL TV, and then Jerry, obviously, you have, and if Larry's out there, I'm sure he knows more about this than I do. But what the PAL would do is it would actually flip the polarity of this. If it started going high on one, it'd be low on the other. That's phase alternating line is what PAL means. And it means that this clock would alternate its phase by 180 degrees line to line. And what that does is that actually is meant to cancel out if there's a noise. Anytime you add a positive and a negative, they cancel to zero. So the idea was to, if you flip the color carrier back and forth, it would null out certain kinds of noise, or actually a tint swing. If you change the phase of this, people turn green and orange or back to green. So that's actually the effect that had on a TV set. So we did that by, again, the inertia of the capacitor would hold the 3.5759 megahertz as hard as it could, and then this would just keep tweaking it to hold it on that frequency. So there's a good example of clock recovery. Now, let me see if I can share a screen. That's a great shot.
There we go. Yeah, we can see that.
All right, so here's our two phase lock loops drawn a little better. What we see on the bottom is a real common digital rendition of it, which is forget the other comparator. We're just looking for edges. And remember talking about Bearcat scanners, the scanning mechanism in there, where the light bulbs lit, and that's what determined the length of time it would stay on a channel. Mm-hmm. Well, the old Bearcat scanners, when I was young, actually, if you scanned 8 frequencies, you had 8 different crystals in a radio, and it basically was switching these crystals in and out. And then one day, frequency synthesis happened, and this right here. I don't know if the mouse probably won't come through. I should have made it a bigger one. This is the heart of frequency synthesis, and quite simply, it means if the VCO is running at 8 megahertz, and I divide by 8 and compare it to a 1 megahertz signal, I can make any frequency I want by how I divide it. And in the Commodore 64, they do a 5/8 division, I think. It's something like that. If you do the math of 14.318 megahertz, to get it down to 1.02, they do have a multiply by a number, divide by a number, so it doesn't even have to be integers, is what I'm getting at. So this is a real common form of the phase lock loop, is the digital. But here's why I wanted to show how we can restore a clock edge. And on the top here, Jerry, you know about VCOs, the canned oscillators we have that are so handy when you just need 10 meg or 20 meg. Well, the problem with them is when the rising edges are going to occur, without a doubt. 10 meg's 10 meg, going to occur every, so many nanoseconds. But the falling edge has a spec of it's like 40 to 60%. So what that means is this falling edge is garbage. And this is the way I actually see circuits. I see a hazy, when I look at a waveform, I either see a clean edge or just a hazy anarchy. And so the falling edge of an oscillator that is unknown. It occurs sometime before the next rising edge, and that's really it. And in the Commodore 64, I'll use that example again. Again, I'm an old Commodore, I'm a recovering Commodore engineer, as I say. But Bob Russell, about two or 3 years ago, was commenting, he's like, if we had just had another edge. And he was talking about the Commodore 64 had some real bad DRAM timing problems. And the problem was, we might start RAS here, can you see the mouse moving by
Yes.
chance?
Yes, we can.
We'd start RAS, the row address strobe for the DRAMs, and we'd start CAS here, the column address. But somewhere in the middle, we needed to switch the multiplexers from the row addresses to the column addresses. And you'd think you could use that. Boy, no, it was either cutting too short on the rows or not giving enough on the columns. And then production would get involved, and they would put capacitors on things. And we're going to talk about why that's bad. Because it not only slows down the where this edge occurs, but it actually turns it into kind of a trapezoidal form. And you spend like forever and a day in no man's land between the two voltages, and that screws us up. So, but what the phase lock loop can do, and so this is for home hobbyists here, if you ever need to make this edge, use a phase lock loop. And what you do is, one technique is you go ahead and pull the free.
Uh-oh. I think we may have lost you, Bill, if you can hear me. We lost him. So,
You got me?
All right, we're coming back online. So I think you need to start your video.
Now, can you hear me?
I can hear you. Can you hear me?
Yeah, I'm still throwing an internet connection error here, which.
All right, here's my. Oh darn! I was gonna say very bad.
Now you got me, right?
Okay, I can see you.
Okay. Can you see that? No, probably not.
No, not yet. If we only had NTSC video still, we could just do.
Oh my God. I hate what I have to go through to make this video. I'm so proud that I fixed it with $8 grabbers instead. I had like $400 worth of grabbers the last time we did this. And all right. Is that big enough, or should I go full screen?
I think it's probably if you can go full screen, it probably would help.
Okay, I'll do that.
Excellent.
Okay. So what we do is we run the oscillator at 2 megahertz. If this is a 1 megahertz signal, we run it at 2. We lock the front edges together. Remember that phase comparator? It's all it does is lock these edges. And then I divide it back down to 2 because I know where this edge is too. Suddenly I know where every single edge is. And now instead of this hazy anarchist fuzzy thing here, I actually have an edge I know about, or more importantly, I have an edge right here that's rising. So by taking a signal that I only know the rising edges on, I can turn it into a signal that's got even more information in it. So that's kind of creating a known clock edge using a 2-edge clock. So there's one of the things that a phase lock loop will do for us. I want to talk about taking the skew out of cable. Is everybody following this so far? Am I just rambling, or is this making sense? What are the people saying?
Oh, it looks good in the chat room so far. Let's see what they have to say.
Anybody sleeping?
Someone had a question about RAS, what that stood for. That's row address strobe. That's where you strobe in the row part of your address into a DRAM. Uh-oh. Where's Bill? Yep, people are saying it's excellent. They're following. Looks good.
Yeah, I'm actually trying to turn the camera back on, and Skype evidently likes to share the screen, and it wants my opinion on Skype. It's asking my opinion right now. Excellent. But it's not letting me share the screen. When I click on it, you go, uh-oh. I think I'm starting to hate Skype.
Just go ahead and disconnect and...
I'm clicking on the camera icon. I really am.
If you need to call back, it's fine.
Wow, it really is screwed. Let me call back in. Let me get my video. Oh, wait a second.
People in the chat room are saying that Skype is more buggy than the last few versions, so There we go.
Okay.
I'll do a song and dance over here. Dun, 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 dun.
I can see you, but how come I'm still a question mark?
I don't know. The question mark over your head and that symbol is kind of fitting. Ah, we can see you now.
There. Can you see that now?
Yes.
All right. Well, we won't be sharing the screen a whole lot then. So, yes, I wanted to talk about cable skew. Without sharing the screen, I was going to tell the story real quick of one other time when we synchronized something. And that was for the Commodore CES show of 1985, where we had an 80-column chip, as I was saying earlier, that had its own clock. And it had, and we would put read-write lines and address lines into it, and we would strobe it, and we would go, here, take this data, take all of the data, take all the addresses, because it tells you which register we're writing to. And they came back, and we knew there was problems early on when they did things like saying, well, it turns out it works better if you write the same data twice in a row. And there's stories about damn Texan registers and things about what that meant. But it really started to fall apart. And what it was, let me see if I can draw this. And to this day, I've never, any of my designs have exactly one clock in them. I synchronize everything. I don't care if it's the doorbell, it's synchronized to the master clock. What they had was, there was the 8563, had a 16 megahertz, and then we had the VIC chip. And maybe you can see that, VIC. And he had his own 14.318, 14 megahertz. And of course, the 1 megahertz for the processor came out of VIC. And so when VIC would use that clock to write to the 8563, it looked like this. There would be this nice strobe. And if we were to put that on an oscilloscope compared to this 16 meg clock right here, it would have looked like this. Just breaks. Yeah, I'm still emotional about it 20 years later. There's nothing there, right? Because it wasn't synchronized. And what happens when you try and clock something that isn't synchronized? And we're going to draw something. We're going to draw a clock. We're going to talk about analog and digital real quick. This is in TTL, and thank God 3 volts came along because we were wasting all this voltage up here. We could say it's digital because we call this a 0 and we call this a 1. But what really happens in real life, of course, is the voltage starts to go from low to high. It starts, and usually it's somewhere down here, and it's bouncing around, and the ground on the pin is coming up and down. And so we've got a noise threshold here. If you've ever heard the fact that an OR gate might be noisier than any other, what it meant was you were trying to hold both inputs down in this little itty-bitty spot right here, and even the slightest little spike, well, if you have an OR gate, we know what it is if one's a 0, one's a 1, but what is it when one's an X? It's unknown. And so the second a noise pops above this level, this OR gate will start the path from being a 1 or a 0 and start to flutter and start to become an unknown. So you're going to hear me talk about the propagation unknowns. So as a clock starts this path, he goes into an unknown state and then comes out the top. Now, if this rings, he's not known till the stop of the ringing. So ringing, if you have a clock and it does this, the clock went invalid here and didn't get valid till here. The longer a clock stays invalid, the bigger chance you're going to have for metastability. And what is metastability? Metastability, if you've ever seen a, remember on the old flip-flops, like the 7474s. You ever hear them called master slaves?
Yes.
Well, there's a reason. And we back then we used to be like, oh, is it a master slave? Now it's a given. But what happens in the flip-flops, if you can see the gates here, if this clock gets into this area, this X starts to propagate. So pretty soon this input says, I'm no longer a 1, I'm no longer a 0, and his output says, I'm no longer a 1, I'm no longer a 0. And it comes back to here because a flip-flop is 2 bistable multivibrator. And he goes to X. Doesn't matter what's here, he's at X. He's at X. It's racing around. Well, in the master slave, we've got one more stage. It buys time. These X's start hitting this, and they start to race around. But if you're good to your clock circuit all, by the time that the X's have gotten here, the clock is now high. Everybody settles back down, and you get either a 0 or a 1. So the propagation of unknowns is this condition where the X's start making their way around your circuit. And it's called metastability. It's literally, picture it this way, this is how I see it in my head. If this clock messes up its timing parameter, and that's why there's a rise time on these, if this rise time is 1 nanosecond, you take 3, this multivibrator will multivibrate. It will go boom, boom, and stop. And it's a coin toss where it lands. So at the very least, you've got random information, but during this time, power is spiking, noise is spiking, this guy's getting upset. And in the old ECL days, this could run completely through a circuit in a few nanoseconds. So that's why taking care of your clock is real important, keeping it out of no man's land, keeping these X's out of your design. They're not unknown states, they're indeterminate states. Unknown makes it sound like it's okay, it's a 1 or a 0, we just don't know what it is. No, it's indeterminate, it's somewhere in the middle. So, and this is why putting a capacitor, and this is, if you open an old Commodore 64, production was down there with bins of capacitors, and they were soldering them wherever they could find a spot to try and make them work so they could ship them. So they're soldering them on RAS, they're soldering them on CAS. And what happens is that clock, I'll draw a new one here, instead of being anything like this, starts to look like this. And so it spends this amount of time, huge amounts of time, 5 nanoseconds in no man's land. And so, and then the caps themselves were garbage. And so if you ever look at old Commodore 64s, they had these caps tacked on them, and it all went back to that edge that we didn't have to make good timings.
Were they just doing that on units that failed, or was it just across the board?
They had skids that they would move around of different kinds of, and they wouldn't come ask us. There was actually, when I first got to Commodore, there was a rule that engineers are not allowed in production. And I mean, they were dead serious. The security guards thought they were off-duty mall workers or mall security guards or something. And they would rough you up and stuff. It stopped. After a while, I actually ended up like drinking with the head of production and saying, what's with that? You know, and hey, we can actually help. It's not about blaming. We can actually help you. And but the reason they didn't want engineering down there is they didn't want us seeing all these, what they're doing, soldering these caps all over the place. Because the reality was they were just making it past the test. It would still lock up in 10 minutes of home use or whatever, because it's just a cap. It's a Z5U cap that varies its amount. And so the 128 was the first time where we actually had enough clock edges where we tended to get rid of that, of that problem. So, but, so bottom line is really it's about the clock edge being where we need it to be, being clean, and not being in the garbage, okay? And that will take us to the cable skew thing. Let me show the cable skew problem. So I've told you that a phase lock loop can see the future. It can also predict the immediate past, is probably a good way to say it. Here's the problem. I've seen lots of people do this. Let's call these FPGAs, because they're faster than snot these days. And that's where the problem comes from. If this is a clock driver, and here's some signals going to here, and it's the same clock in both, in theory, you would think, your clock would go like this, all the data you'd been holding would hang out for a short period of time right in here, if you can see that. So the clock goes high, and new data starts to come out. And the idea is that he latched it on the same rising edge. So does that make sense, Jerry,
Yes.
so far?
Yes.
All right. So people, the engineers, they'd hook these together going, we saw the same clock, so it's very valid to use that clock to latch his data on my rising edge. And that'd be true, oh man, it's so close. What's happening is these speeds are so fast, the speed at which you will go indeterminate is so fast that it's the capacitance of the pins that's getting involved now. This thing, we actually call it -1 in the school I'm from, which means if you ever do this, if you see somebody try and make a delay with buffers, right? That you would think that that'd be 2 or 3 nanoseconds of delay. Inside a package, by the time you get involved with all the routing variables and the pin capacitance, this could have a delay of -1 nanosecond. In other words, it's not useful as a delay. So you'll see that I just think like this, that you cannot create delays this way, and that the delays of modern circuits are so fast that it's really about the physics that are involved. So you would think, well, wait a minute, what if I wired this so the clock got to here first and then here, right? Let's say I fed it from this end. Well, if this is a transmission line, I'll tell you that this one actually saw the full voltage first, and this one had to wait for the reflection to return, because in the meantime, it's a voltage divider, especially with the resistor here. So you move the problem, and you might make it work, but at the end of the day, we call it the cable length problem, and that is you're just on the hairy edge from having tons of setup time to having no setup time. Also, this clock moves this way 1 nanosecond, and you're into the crap. So that becomes the problem. And this works across cables too. If I clocked data and it goes across the cable, and I sent the clock across the cable with it, let me redraw it. So it's like, that should work. I clocked him, and it's the same clock. It took the same path the cables did. Whether these are data lines or read-write lines or something like that. I should be able to do this. Well, your first indication that things are going terribly wrong is when the length of the cable matters, because you're starting to get into this clock wiggling back and forth based on some factors. Namely, there's a lot more capacitance on these a lot of times. Sometimes there's a lot less capacitance. And the worst example of the cable length problem I had, or ever heard of, is I knew a girl that worked on the Aegis radar system for RCA in Morristown, New Jersey. And we were on an ambulance squad together, and we're sitting there one night. She said, oh yeah, we had a problem. We had to shorten or lengthen the cable because it didn't work otherwise. And her problem was that in the Navy, you're not allowed to have extra cable coiled behind something. So they actually had to move a piece of equipment on the bridge because they wanted to make the cable shorter or longer. And I forget which. So it's like they had to make it go a foot further to the right. They had to move the cabinet a foot further to the right. And I told her, I said, it won't work. I said, without even knowing what she's talking about or what the problem is, I said, you're clocking the same data as going across the cable. It's metastable, and it won't work. And 2 years later, I ran into her, and I did ask. I said, so how'd that move? She said it didn't work. And so here's the Navy and RCA all learning the hard way that you can't use the same edge and send it across here and expect it to survive this trip. So, well, what the heck do we do? And I had a drawing. Maybe I'll try and draw it. One of the things we can do is we go ahead and we look at the future. That is, here's our phase lock loop. And I go ahead and I send a clock across the cable. Right, so here's our cable connector. And then what I do is I bring it back across this cable, and I put it in the phase lock loop. And here's our main clock. That's a horrible drawing, but you're going to have to live with it. Here's a nice version of it. Let me draw it again. I'm going to show the cable, how we can see the future. So we've got a cable end here. We've got a cable end here. And then we've got our clock. So what we do is we can loop this clock back, and then we can actually do this on a PC board if it's big. Or any other condition where maybe there's a lot of capacitive loading on it or whatnot. So we bring that back to the phase lock loop. Now I'm in the glare, aren't I?
Yeah. I think we can see it, though. Oh, excellent. You got it.
And then we compare that to the clock we had. And what will happen is, here's the edge that everybody else sees, right? So we know where that edge is. Well, it's going to move, and the oscillator, the VCO would have started here. It's going to keep bringing this back earlier and earlier in time until the round trip lands us back on this edge. So what we have is now a clock that is earlier. It is known to get there before everything else because it already made the trip twice. So, and sometimes they'll call this a delay lock line. So that's the one thing. And this, like I said, this can be on a board. And the real way to fix this is, these days you don't do a daisy chain of clocks. They'll do very controlled, skew regulated. They can even regulate, you might even trim them and tune them. Jerry, what experiences have you had with adjusting skews? We were talking about some of the SD RAMs or something doing that.
Modern DDR style memory
That's it. Yeah.
Has a initialization stage where these drivers go through a particular pattern, send it to the memory, and then they read the value back. And they skew them back and forth, and then they find the sweet spot where all the data lands, and then sets it dead center, and then that's what your driver's delay will be. So each pin gets adjusted.
Because there's no right answer otherwise. You can't predict it between all the parts variations. Temperature, I'll tell you, you might say, well, hey, those two FPGAs side by side, how come their clocks are different? One FPGA might be hotter than the other. I mean, you can't predict. One might have a slight standing wave. One might be the last, there's so many little things that were on the hairy edge that you can't use the same clock pipeline like that unless you're real careful. I've been known to just flip the clock and go with it that way to cheat. But this phase lock loop, that's why I say it can see the, because it'll actually sense that. And if we had the my other laptop on the Skype here, I was going to walk through the Altera phase lock loop symbol. And it's pretty cool because it's how many outputs you want. And it's just like you said, what frequency would you like? And then you even get to adjust the phases and the duty cycles and all that. But at the end, it says, which one will I monitor? And that's the one that's inside that feedback loop that we saw going across the cable. The same thing applies on a board. It's like, who do you want me to sync up to? And those edges will be just dead nuts on.
You have to be careful with some of these FPGA tools. I ran into a situation recently where I entered a number and it said, okay, we can generate that clock for you. I'm like, wonderful. And then the design didn't work, and I went back and I looked at the log files. Well, it said that it could make that clock for me, but in actuality it was, for instance, like instead of being 1.000, it was 1.0001. Because all it could do to get the dividers right, and if you don't really look closely, it can come back and bite you.
And then there might have been 373 flip-flops to make that divider instead of 16.
Yeah, who knows?
Or the interim frequency might have been 800 megahertz, so that it could divide it down into the integer. So you said it, and asked the group if the thought that I had was if people want to learn FPGA design, we could do this and actually walk through. You can download Quartus from free from Altera. You can the Xilinx tool. I tend to be more of an Altera guy. And install it on your laptop. And the biggest thing is, I hadn't run one in years. They moved all the stuff around, but I just knew that it had to exist. That's the only advantage I have is I go, oh, no, I know there's a way I can set the thing, and I keep plucking around until I find it. So if people want to learn how to do their first FPGA, I mean, I've got this is Terra ASIC, and the board itself is like $129, and it's got the USB blaster built in, toggle switches, everything. I mean, I run high definition video with a different plug-in on this that cost another $100. So the kits are just, geez, we used to have to spend $30,000 or $40,000 to get that kind of tools, and now they're free on the net.
Yeah,
But with what you go ahead.
oh no, yeah, that's great. The tools are, that's the only reason I could get into doing chip designs
That's
because
it.
the
Yeah.
tools. The first tool I bought was a couple $100 from Lattice, and then Altera and Xilinx came out with their free tools, and
Yep.
and they're actually better than ASIC tools in a lot of ways, to tell you the truth.
Oh, yeah, and I'm from the days when there were no ASIC tools and were no ERC checkers. We'll have to swap stories sometime.
So
When I
you're so
started,
you want to ask the chat room if they're interested in seeing a regular episode of Bill and FPGA funness.
yeah, do your own FPGA on a laptop, learn how to do one yourself type thing.
Yeah, the chat room's
Because
going
we're that,
crazy right now with different boards that you can buy for $50,
yep,
$60, and
yep,
there's lots of
yep.
them out there.
And what made me think of that though is what you said. You can't trust they're tools, and you got to learn the difference. Just because the simulator worked, oh, that just corrects the herd stupidity factor in my head. That means I didn't get my terms inverted. But then the real task starts of, we know that if you don't hook a reset line to it, it won't know how, it thinks everything's an X and it keeps propagating X's. Well, it didn't really happen that way. It
No.
started with a 1 or a 0. There's not X's flying around. But we have to tell the simulator, do this. Well, so then we think that, oh, it starts up like that. Well, no, it doesn't do that either. It starts up some crazy-ass way.
I just shipped a design about 3 weeks ago that I ran it in the simulator, showed that it worked in simulation. The client checked off on it and said, yes, this is what we're going to build. We built it. Didn't work. Ends up that it was a battery management system, and they had it hooked to a big toggle switch. And when I ran it in the simulator, to simulate, I'm like, well, probably has a mild rise time on the voltage input. No,
Instead, it's going bang, bang, bang when you flip the switch.
and it's one of those things that, it looked great in simulation, but didn't work in the real world. Luckily, it was a pretty easy fix, but, as soon as they told me, like, yeah, we hooked it up through this big toggle switch, I'm like, okay, I better
Yeah.
check rise times.
Hey, get the old Commodore 64 production crew to solder some capacitors on your toggle switch for you. Because they would. I mean, let's slow it down if that's the problem. So,
Well, actually, that was my fix, changing some capacitors around, but
the I liked what you said because I called you a while back and said, well, what's the standard for how you turn in your work? Because I do this as playing around these days and whatnot. And I liked what you said about sending the test bench with it, saying here's it's kind of like a math equation and the proof both, and it almost doesn't even matter if it worked. It matters if it acts the same after they've installed it in their core or in their circuit or whatnot.
yeah, I almost always want my client to sign off on some kind of like primitive simulation. And they should pay for that up front, get me to do that part of it. And once they feel all happy and warm and fuzzy
Proof
about
of
it, then
concept.
we go and we actually produce the actual boards or the design,
Right.
and at least there's no surprises. Like, well, this is what you guys signed off on.
Yep.
So the
Yep.
chat room says absolutely. I saw tons of yes, we want more.
Okay.
So
Because, yeah, I mean, just even the PLL macro, the primitive we could go through today, and everything we talked about sitting right there like beached whales just waiting to be clicked on and checked. And you can put in the divide down chain, or you can just tell it the frequency you want, and it does the math, tries to do the math for you.
well, I think you did a great job explaining the basics of PLLs. Only a couple little glitches there in the audio, and I think we'll just upload it the way it is to YouTube, and I won't worry about trying to edit the few minutes of issues out of it.
Yeah. Then watch it all the way through and find them.
So you want to answer a couple questions in our
Yeah,
last
I was
few
going to
minutes?
say I'm kind of spent. So what kind of questions or where did I screw up the most at, and we'll see if we can patch it.
Okay, let's see what the chat room has to say. There's a little delay in the video, so we're running 3 to 10 seconds behind here. So great
Frickin'
stories, by the way, about the Commodore days and the capacitors and
Oh man, they It's not fair that 3/4 of my stories of a 50-year life are from a 5-year period, 4-year period, but they are. You know, we
Okay,
lived in time compression mode. Go ahead.
so Jack asks, stupid question perhaps. I thought a VCO was analog. How could you put the PLL in an FPGA? As in, I guess he's implying since a FPGA is digital.
It is so important that they found a way. Seriously, it is. It is. You cannot do this high-speed stuff. These outputs are then feed the LVDS, low voltage differential drivers and everything. Um, if they said go find an analog PLL and make it work, you know, they even use the PLL inside the chip, you know, for routing and things like that. They'll sample the signal on the other end. So you're absolutely right. It's analog, but at the end of the day, it's gates. Gates are on and off, and they can be in the middle somewhere. And so it is an analog component that's on there.
I actually have a bit of a story around
Yep.
adding PLLs to digital chips. It is analog on there, and it's a significant part of the die to have
Yeah.
these analog transistors and circuits on there.
Often. Yeah.
Whenever I do an ASIC design, that's a big consideration. How many PLLs are we going to have,
Yeah.
and how are we going to manage noise on the pins because these things are bouncing around and consuming a lot of power. They're producing a lot of heat. So very analog on a digital chip.
Okay. Let's pick up on that real quick. If you had a single frequency for your computer, guess what? It'd broadcast that single frequency. So what we're doing with computers these days is spread spectrum on the clock. The clock's actually doing this so that when you listen to it on a scope, you don't see a single spike at 100 megahertz. You see it wash. As it washes out, the spikes come down and you get a spectrum. So that's why they call it spread spectrum. So even on your PC, it's 2.6 gigahertz. Well, give or take a bunch. They're shifting it around. So for that very reason you just mentioned.
So here's a question more about your bench. Is that an Elenco on the shelf back there?
LMCO. What's an LMCO?
Elenco? Elenco.
For which part? I actually bought this all on eBay 15 years ago when eBay first came out. I was like, ooh, ooh. And by the way, you mentioned an oscilloscope. My favorite scope of all time was still the 2465 because it had a NTSC. I could actually tune in horizontal line 17 of the odd field. And that was heaven for a guy like me, because otherwise we had to do real tricky stuff to get in there. This is just an old Tech Logic analyzer that I can actually use a USB thing with. That's a signal generator, NTSC now obsolete, HP counter, HP signal generator. Oh, goes a gig. I didn't know that. And I have a spectrum analyzer down here. I can't even lift up this little scope that I was showing you. Whoa, that's what fell earlier.
Crash.
Crash. This thing here will do an FFT. Yeah, kiddo. So I actually have the ability to do spectrum analysis without getting this huge, heavy thing out. So it's amazing what we've got to play with these days. Back when I was doing hardware engineering, you couldn't do your first piece of work without $20,000 worth of equipment. That's why I went out and bought all the eBay stuff, including 2 or 3 scopes.
I see what they're saying. The Elenco teaching electronics kits. They must be talking about
Oh, hey, that thing. Yeah, well, I'm actually this thing right here. Is that what we're talking about?
I think that's what they were asking about.
Yeah, I bought this for my kid. I got my start in electronics. I still have the capacitor from it, and it's 45 years later or something like that. I got my start in electronics, and then I'll answer the question of the brand because I don't know. My dad brought home a 201 project kit for me, and up until I burned out the NPN transistor, I was making solar beepy things that transmitted to the local radio and everything. So, and I taught myself a transistor. A transistor is this, right? A little bit of base emitter makes a big base collector. So when I look at a schematic, you see all this going through. Well, I taught myself that. There was nobody to teach me, and I learned it from a kit. So, of course, I got one for my kid. And we actually troubleshot for the schematic being wrong, which I loved. It's like, aha, you can't, you know, it didn't work because the resistor value is wrong, because the schematic's wrong. Now, what do you think it takes to make it work? So I was pretty cool with that. But this is a, let me throw it on here. This is Maxatronics 501 electronic kit. It's actually got a little bit, what we used to call a bits-like processor. There's a processor in it. But I used it for the breadboard and the fact that, here, let me turn off this. It's got a very quiet power supply. They're AA batteries, and they tap it so you have a 2, 4, 6, 8-volt source on it. And so I just brought it out so I'd have something to show with this. But it's actually my boy's. I got to give it back when I'm done. It's a little CPU on it. There's cadmium sulfide and then a faster transistor. Wow, you could actually compare the speeds of those. And switches, lots of switches and a hex keypad and everything. So, you know, it's a toy, and it's more powerful than what went up on the first shuttle, I'm sure, as far as the processor in that thing.
So they want you to write a book, tell more of your Commodore stories and other fun tech stories. Someone said they want you to do a calendar, so I'm assuming they want centerfold pictures of you or something. You guys are sick. You guys are sick out there.
Yeah, Greg Berlin had a pipicture, caught a picture of me in a Japanese bath. I'll just end it at that he got through customs. So there was one in the old days. If there's a co-author out there, yeah, let's talk, because I still remember the stories, and you know, a lot of them are verbatim in Bagnall's book, but there's the first person part of it, and I always start my stories with my, you know, sitting in a conference at Commodore where Shiraz had thrown me in this room and said, here, make a deal for DRAMs. And I've been looking at the timings for a week, and so I've got my calculator, my HP, my Pride and Joy cost me $200, had the real tiny 0.3-inch LED, and you had to twist it for the numbers. So you would twist it till the number stopped flickering, and that'd be your answer. And they put me in this conference with these guys from MOS Technology, and they're going, well, if you move the RAS, remember road dress strobe time, if you move the RAS and we have pre-charge time. I'm like, tap, 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 what? Tap, 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 you know, and I'm writing, I'm trying to keep up. And right in the middle of this, my calculator stops, because it was actually only good for about 8 minutes off the charger, as it turns out. So even twisting it wouldn't work. But I didn't let them know. So I'm standing there, I'm watching these guys. And I look up and I realize they're playing poker with me. So I'd say, well, if I move the RAS, and you'd see them, I'd say, oh, we bring it back, and they'd settle down. I'm like, they're playing poker. Oh, it's not about the numbers. So I said, guys, what is it you need? You fucked something up. What is it? And they said, oh, we need, oh, no problem. You give me pre-charge time, you can move the RAS. And we became friends. That was Greg Clotter was in that meeting, I remember. And so that started the process of MOS and engineering not hiding things from each other, but we'd say, show me the shmoo. And they'd show me how they said, we meant to make the shmoos where you change 2 variables at a time and you get a plot. And shmoos are like cartoon characters from before I was born. But they'd show us they meant to make the chip this way and then be this way. I said, okay, I can adapt the design to that. Thanks for showing me. By the way, can you relax the temperature when you know, and we would trade off like that. So there's that wonderful first-person experience of a kid completely out of a high school dropout, found his way in Commodore, and his calculator stops working. I'd love to be able to tell some of those in first-person stories. So yeah, if there's a co-author, you know, a ghostwriter out there, that'd be cool.
All right, we're at our 1 hour mark, so cool. I need to kill the recording.
You need to get back to work, young lady.
Yeah.
How old are you now?
21. 21. So, how can people get a hold of you? Quickly
Bill
changes.
C128.com works. BIL at C128.com.
You're on Facebook and the Twitters and all that stuff too?
Yeah, I'm linked to your page. Hey, everybody that's listening, go join my Facebook thing, so I get lots of things, and people think I'm important because I have a lot of Facebook friends.
All right, I gotta cut this off so we can get it onto YouTube. We're at 59 minutes and 23 seconds.
And you have a software radio you have to get done. You'll have to tell me about Meet and Grad in Mahara, why you did it, where you were at, and what all those pictures are.
Oh, yeah, I will. Okay,
all right.
Thanks for watching, everyone.
And let's talk to FPGAs or something in the future.
All right.
Take care.